All right, chemists, welcome back. So this week is the first time we'll have a midterm quiz. There will be 2 total in addition to a final exam. And the midterm quiz will be on Friday during regular lecture times. Okay, so it will be 10 o'clock on Friday. And the duration of the quiz will be 50 minutes, the same time as the duration of the lecture. The quiz will be in Canvas. So at 10 o'clock on Friday, you'll be going to Canvas to click on the midterm quiz, which will be quite evident. It's directly on the opening page of the class website. So you just click it and you just do the quiz as if you do the homework exercises, the homework assignments. It's very similar, in fact. The types of questions are very similar, and the format is also identical. Okay, so that will give you an idea of what to expect. In addition, later today, we will be posting a so-called practice quiz. Okay, so this is a quiz that contains questions of midterm questions that were given in previous years. Okay, so this is a collection of questions. It's not representative of the actual number of questions that you will be getting, because what I did for the practice quiz, I combined 2 previous exams into one. Okay, so it's about twice as long. So don't get, kind of like flustered by the length of the exam, because it's twice as long as a regular exam. Okay, but at least it will give you some ideas on what to expect, and also will give you ample practice problems to look at. The key to the practice problems will be posted later this week, but I want you to just play with it, just try it, just pretend it's a real test, so you can see where you're at with the material. Okay, so on Thursday, I guess, I'll be posting the key to the practice problems. In addition, there's also already on the class website an extra sheet with bracket problems. Okay, so the bracket problems, we just introduced it on Friday. I just want to make sure people are familiar with the notation, and that sheet will contain some problems with the answers, so you can see how it's done, and hopefully that will give you some additional practice opportunities. So also right now, actually, I'll say a few more things about the bracket notation, and hopefully you'll agree that it is a notation that will become very important and handy as we move along. So yeah, the exam is mostly multiple choice. So the questions you are getting for the homework are very representative. And again, the practice quiz that you'll be looking at this week, which is not graded, it's just purely for practice. So just go ahead and make mistakes. It's fine. It's for practicing only. Is very representative. So just look at those, and then you should get a pretty good idea of what to expect. That's the format that we'll be having for the midterm quiz. Okay, so I'm going to dive in right now. I'd like to kind of get back to what we talked about on Friday. It's a couple of things that I was not happy with the way I explained it. So I'm going to quickly go over that one more time, and then we'll just be introducing a new situation, which is actually the movement of an electron or a particle on a little ring. Okay, and this will bring us a little closer to the situation that we're really interested in, and that is the motion of an electron, or the state of an electron as it is when it's bound to an atom. Okay, so let's look at the following. We looked at the harmonic potential last Friday. Okay, and some students were asking, why is this important? And it is important because the harmonic potential is the kind of potential that is relevant to vibrational motion, right? And vibrational motion in chemistry is very important because vibrational spectroscopy, such as Raman spectroscopy or IR absorption spectroscopy, basically measures the vibrations, the energy of vibration as 2 atoms move relative to one another in a molecule. Okay, so these vibrational motions are relevant to chemistry, and the harmonic potential basically describes how we should understand such motion and the energy levels, the quantized energy levels that follow from that. Okay, so that is the relevance. So What I said on Friday is that if we have a potential well like this, the lowest energy state, which was nu equals 0, looks like this approximately. And if you go higher up the potential well, so I'm going to go higher up in energy, then the wave functions will change their shape. Okay, in fact, you see more oscillations on the edges. Okay, so you see here on the edges, if you go higher up the well, there's more probability near the turning points. Okay, so the electron will spend a little bit more time at the edges and not so much in the middle. Okay, and this is, of course, what we related to more classical behavior. Okay, so in classical mechanics, if you have a pendulum, your pendulum spends more time at the turning points and less time in the middle because there the velocity is the highest. Okay, so we also said that the average or the expectation value of position is basically 0, because if you draw a line here, okay, and do the probability of all the wave functions, you'll see there's a 50% chance that the particle is on the left and on the right for all wave functions. Okay, all the wave functions are either symmetric or anti-symmetric, but if you do the probability, which is the modulus square, you will find that the modulus square of the wave function is always symmetric around 0. Okay, so this is x equals 0. So therefore, the mean, which is the expectation value of the position operator, is expected to be 0. We also saw that the square of the position operator, its expectation value is not 0, okay? And it is in fact related to the potential energy. Now, I want to give you a little bit more of a physical feel for this, because I think it was not communicated well by me on Friday. This quantity here is called the mean square displacement. What is the mean square displacement? Well, it's already in the description of this quantity. It is the average displacement relative to the mean. Okay, so the mean, as we concluded, is kind of 0, spends as much time to the left and to the right. But the mean square displacement is the average displacement that it has away from the mean. Okay, and that's exactly what is basically described by these turning points. Okay, so you can see that the extension away from the mean is larger if you are moving up the well, if you go to higher energy states. Okay, so it will have more time spent farther away from the mean, which is 0. Okay, but it's equal on both ends. Because it's equal on both ends, the average is 0, but the mean square displacement is not, because the mean square displacement is a measure of how far the particle can be from the mean. And that quantity goes up, of course, if the particle has more energy, because it can basically extend more. Okay, so that is what is x squared and then expectation value of that means. This quantity is not 0, and it shouldn't be 0, because you can see it from the picture. That quantity should go up as you have higher energies. Okay, so if you do problems with this, you will find indeed that if you compute this quantity right here, that it's not 0, and that's one thing, but also you should have a little bit of a physical feel for why that is. Okay, so two things are important: to do the math right, of course, but more importantly, to actually understand why that is so. Why wouldn't you expect this quantity to be 0? To some people, this is confusing because x and x squared looks very similar, but in fact, it's not. Okay, the mean square displacement and the mean of x are very different quantities. So this is definitely not the same as the square of the mean. Okay, these two things are not the same. So please differentiate between the two. Okay, so that was one thing I wanted to kind of like clean up, if you wish. And the other thing I'd like to say is about the bracket notation. Okay, so let me just move to the following here. There we go. Okay, so here is a general operator. Okay, we know this operator has eigenstates. Okay, let's say the eigenstates are phi n. Okay, we're familiar with that notation now. But now I'm going to say the only thing I really need to know is not so much phi, what the phi looks like. I'm just interested in which number it is in the complete set. And that is given by just the index n. So I can write this as a ket function. Okay, that's the ket notation we introduced on Friday. And just the n is enough to let me know which function in the set, the complete set of eigenstates, I'm talking about. Okay, that is sufficient. I don't need to write the phi. So I'm going to be as shorthand as possible. So anytime you see this bra or ket with a number in it, number n, an integer, it simply is the label of the function of the set that is found from this operator. Okay, so here it is. I can now multiply, let's say, this bra with the ket from the left. Okay, so that's what I'm doing. I'm taking the bra, I'm going to multiply it with another function from the same set. Okay, so m and n are two functions from the complete set of eigenfunctions of this operator omega. Okay, so this will be an integral. This represents an integral, an overlap integral of these two functions. And we know that that should be 0 if these two functions are not the same. Okay, so that is the Kronecker delta m comma n. All right, so if I now do the following, I have the operator, and I'm going to operate on its eigenstate n. Okay, so that will basically produce an eigenvalue. Let's call that little omega with an index n, and then the function again. Okay, so this is the eigenvalue equation for this particular function in the set, the function n. Now what I can do is I can do the same thing. I'm going to multiply this thing from the left with the bra. Okay, so with this m. So m again is a function from the set, but now the operator is sandwiched between them. Now you can see that what happens is I have, of course, the operator operating on n will produce an eigenvalue. And the eigenvalue is just a number. So the number I can take out of the integral. And so what I get is the number. The integral is the same as the integral above it. That is the Kronecker delta. So what I'm getting from this operation is a number, omega n, times delta m comma n, right? And we know that, if m and n are not the same, this whole thing is going to be 0. It's only non-zero if m and n are the same. Now, I'm going to define here a new operator, which looks very scary, okay? But let's not get flustered by this. Let's just assume that this is just a notation, and I'm going to just work with it and see what happens. Okay, so what it says, it is a sum over m. Okay, so those are, of course, the states in the complete set. And I have first the ket and then the bra. That looks very weird. But you will see this notation actually is very convenient, and I can do some really interesting things with this. So here is now the same. I have an operator. It looks like the one I just defined, but I'm going to sandwich that thing in between m and n again, just as the expression above for omega. Okay, so now I have an explicit form of the operator. I'm going to just put that thing in there. I'm going to write it out. Okay, so just put that thing above in this expression, and what you'll see is this. Okay, you see the m in the middle, m in the middle, and then I'm just going to sandwich that whole thing between m and n. And of course, this summation sign I can take out of the integrals. I just have to sum all of the outcomes over m. So this looks scary at first, but don't be afraid, because it turns out this is actually not so difficult, okay? Because this thing is simply an overlap integral with an eigenfunction with itself that is 1, okay? If it's a normalized wave function, which you can assume here, that is going to be 1. This is, again, my Kronecker delta, okay? So what I'm getting is this, okay? And the Kronecker delta says, well, if I sum over m, the only contribution from the sum that is non-zero is when m equals n. Okay, so that means basically what I'm getting is the only surviving term from that sum is going to be the overlap integral n with itself. And that's going to be 1. Okay, so that is interesting. This is always 1. So the operator is defined above here. If you do this operation on it, if you sandwich it between two eigenstates, which are dissimilar or similar, it doesn't matter, the outcome is always 1. And that's why this operator here is called sometimes the unity operator, okay? Because the outcome is going to be 1, as you can see. This is just kind of one example, okay? So there's many of these. The other thing I'd like you to show is the following. Right here. Okay, so if I have the same situation here, and we talked about this last time, oops. And then I'm going to take the complex conjugate of this. Now, what we saw last time on Friday is that is going to be looking like this. So the position of the bra and a cat are switched, and the operator acquires a symbol, a dagger symbol, and the dagger symbol is called the Hermitian conjugate. Okay, so if we take the complex conjugate of one of these integrals, one of these sandwich integrals, then what you get is the expression on the right, where the labels m and n have been switched. They have switched position, and the operator now has a symbol, the dagger, and that means the complex conjugate. Okay, so another complex conjugate, the Hermitian conjugate, the Hermitian conjugate. Okay, so now if the situation arises where the following happens, okay, if, I'm going to write this one more time, take the complex conjugate, and what I'm getting is the following. Okay, so basically the dagger symbol is not here. And that basically means that for this particular operator, for this realization, if this is true, that means that the Hermitian conjugate of this operator is the same as the operator itself, following this definition. Okay, so you can see if the following is true, if I take the complex conjugate of the expression on the left, I switch labels, but the operator is the same in both cases. Okay, it doesn't really change its, its sign, so to speak, or the Hermitian conjugate sign. It's the same as before. If this is true, that means that the Hermitian conjugate of the operator is the same as the operator itself, as the original operator. Okay, and that is an important case, because that is the case for all operators that are called, very originally, Hermitian. Okay, so all Hermitian operators have this property. Operator, okay, there's an A missing there. Okay, so a Hermitian operator is defined by the expression right above it. If that is true, then we can say that the operator is Hermitian. Now, why is that important? Why do I say this? Well, I say this because it turns out all observables of operators, such as energy, momentum, position, all real observables for operators that produce real observables, those operators are Hermitian. Hermitian operators produce real eigenvalues, okay, real eigenvalues, not complex ones, and these eigenvalues typically correspond to real observables. Okay, that's why it's important. So an operator like the Hamiltonian is, in most situations, is a Hermitian operator, because it must produce a real eigenvalue, okay, that has meaning. Okay, so that's why I'm pointing this out. Okay, so let's move on to something else, and that is the next physical situation we will be considering. Okay, we talked about a particle in the box. We talked about a particle that's inside a harmonic well. Okay, but now we're going to be a little bit closer to the actual atom, and that is considering the motion of a particle on a ring. Okay, so this is not quite a circle yet, or not quite a sphere yet, but it's just a ring. Okay, so let's say that is the main axis, and the particle is moving on a ring, let's say in one direction. Okay, and it has a distance r as well, away from the origin. So what can we say about this type of motion? Okay, this is a circular motion, if you wish, rotational motion. And let's relate this to what we know about translational motion. Okay, so I'm going to make a little table of the unit and some quantities that are relevant. Translational That's what we've talked about so far. But now we're going to talk about rotational. Okay, so the unit of mass, or the quantity of mass, I should say quantity. Quantity, that's better. Quantity of mass. In translational kind of mechanics, we simply indicate that by m. That's the mass, okay? There's nothing mysterious about that. But in the rotational frame, so to speak, a more useful quantity turns out to be the inertia. And that's something that you are familiar with, hopefully, from regular mechanics, physics courses, okay? So what you see here is m times r squared. The r, of course, is the radius of the ring. M is the mass, okay? So the inertia on this ring is m times r squared. The momentum, it was typically indicated by P, which equals m times v. This is a v now, this is not a nu, okay? That was the translational definition of momentum. But rotationally speaking, we don't talk about this so-called linear translational momentum, but we talk about angular momentum, okay? And that's indicated by a different symbol, that's L, and that's defined as the moment of inertia times a quantity that's called angular velocity. How many times you are circling around that circle, okay? That is omega. So it looks a little different, as you can see. It's not m times v, it's actually I times omega, but they serve the same functions, right? The m serves the same function as the I, and the v serves the same function as the omega. Okay, last quantity, kinetic energy. Kinetic energy is P, this is classically, okay, P squared over 2m. And of course, if you do that, if you write it out with the expression above it, you get this expression, half times m times v squared, very well known. Now, what is it in the rotational frame? Rotational frame, you can say, okay, that's L squared over 2I, okay? We know that L serves the function of momentum, I serves the function of m, okay? So what I get then is half times I omega squared, right? So those are the quantities that I will be using for rotational motion. I won't be using P and M, but instead I use L and I, okay? All right. So let's look at what that means for us here. Come on. There we go. So this is the situation that I'm considering. I have this frame, which is defined as the z-axis, and I'm going to spin around the z-axis with this particle, the green particle. I can write my x and y coordinates as well. But what I'm interested in, of course, is not necessarily writing this in x and y, but consider this as a function of r. Okay, so that's what I'm trying to do here. So the Hamiltonian, in terms of x and y, is similar to the two-dimensional Hamiltonian we've seen before. Okay, so there's this h bar square here. Sorry, h bar square divided by 2m. That is always there. And then I have the derivative respect to x, second order term, and then the derivative respect to y. So this is the general expression of two-dimensional motion in x and y. This is a two-dimensional motion because it's a circular motion in the x and y plane. All right. Is there a potential energy term? Well, there could be, but for now, we're going to say the potential energy contribution is 0 anywhere on the ring. So there's no barriers. There's nothing that the particle will encounter. It's free motion on this ring. Okay. So what I'm going to do now is not write this in terms of x and y, but in terms of r. So what I'm trying to do is to write this in terms of polar coordinates. Polar coordinates, as you know, can be defined as r times cosine of the angle that it's going to make. Okay. And this is the sine of the same angle. What is the angle? The angle is basically the angle defined here. Okay. Origin, let's say it starts at the x-axis, then moves and spins around And as the angle grows, so grows phi. Okay, so that is kind of the definition of phi. So the question now is, can I rewrite this Hamiltonian in terms of r and phi? Not x and y, but in terms of r and phi. The answer is, of course, yes, you can do it. I'm going to show you the result, and there's no need for you to do that by yourself, so don't be afraid, okay? Because it's other people have done it for you. If you want to, you can totally do this if you want, if you spend some time, but that's not the purpose of this course. So I'm going to give you the result. This is what it looks like if I'm rewriting the expression above, which is defined in x and y, in terms of r and phi. Okay, you can see it looks a little different. Instead of 2 terms, I have now 3 terms. Okay, so that looks always a little scary. But in our case, we can make a simple approximation. It's not really an approximation, it's a correct statement, in fact, that if motion on the ring is happening at a constant radius, so r is constant, that means that all the derivatives with respect to r are going to be 0. Okay, so that means that the first 2 guys here, this guy and this guy, simply will be 0, because there is no change as a function of r. There will be no change along r. There's only going to be a change in terms of phi. The phi angle is the only thing that changes if the particle is moving in a circular motion. Its distance from the origin will not change. It will always be the same. Okay, so therefore these 2 guys are going to be 0, equals 0. That cleans up the whole thing quite a bit. Okay, so what I'm having here is the same expression. The r squared, if you see here, let me just circle it so everybody can see it. This r squared here, I take all the way here and put it in front of the m, and that's why I have 2m r squared here in the denominator, and then the second order derivative with respect to phi. Now I can clean it up just a little because you may recognize that mr squared is going to be 2i. Okay, that's the I we just defined on the previous slide. So this is not going to be my Hamiltonian. So I have here an expression of my Hamiltonian in the case that there is no potential energy barrier experienced by the particle. And the question is, can I solve this eigenvalue equation for this Hamiltonian and see what the eigenfunctions are going to be? And the answer is, of course. Let's do it. Okay, so let's do it over here. I have the Hamiltonian, and what I'm going to do is I'm going to try to find the eigenfunctions of this new Hamiltonian. Okay, so this is what it looks like. I'm going to define this function here. It's basically a big capital phi. Okay, so that's going to be my eigenfunction. I have h bar over 2i, then the second order derivative with respect to phi, and then of course the function itself. Okay, and this must be equal to the energy times the function. Oops, that's not right. It's regular phi. Okay, so the capital phi is the name of the function. Okay, capital phi is the name of the function. Little phi is the variable. Okay, that's the angular motion. The angular motion will happen along phi. Okay, so this is my eigenvalue equation that I like to solve. I can rewrite that a little bit and basically isolate the function on the left. That is the second order derivative, and then put all the constants to the right. So I get minus 2i e over h bar squared, and then the function again. Big phi is the wave function I'm trying to find. Little phi is the variable. Okay, so it's the same, and this I'm going to make the connection here. Previously, we looked at an equation as a function of x. This is the particle in the box. Okay, and what we found is 2me over h bar squared. This was the function we were trying to find, solving this differential equation. Okay, so the lower, this one here is a particle in the box. And this one here, above it, is the particle on a ring. It looks like exactly the same. The main difference is that the I has now taken the role of the M, right? And you can also see that big phi is simply the wave function. It doesn't move along x, but it moves along phi. Okay? So what is the solution of this? Well, it looks very similar to the solutions we found before. Okay, so basically the solutions are the following. This is the function I'm trying to solve. And instead of writing the function as a function of x, I write it as a function of phi. Okay, but the mathematical shape is really the same. Okay, why can I? Okay. So that's my general expression. Okay, what is this ML? The ML was previously K. Okay, now it's like a little m, which I call the number that I'm trying to retrieve by solving the differential by solving the boundary conditions. Okay, so the definition of ML equals 2I e h bar squared. If that looks scary to you, remember that previously we had K, which was exactly the same. Okay, remember this one? That was the K. K and ML serve exactly the same function. We found K previously for the particle in the box in linear motion by solving the boundary conditions. That means that this ML you probably also want to solve by finding the boundary conditions and then solve the problem for those boundary conditions that we find. Okay, so the question is, can we define the boundary conditions and then solve for this ML? If we know what ML is going to be, I know two things, namely the actual shape of the wave function, because now ML is going to be defined. And secondly, I also know the energy, because the energy depends on ML, right? I know M, I know R, 2, I know, of course, and then h bar squared. All of these things are known except for the energy. And so as soon as I know ML, I also know the energy. That means I solved the problem. So the only thing we have to do is to determine what ML is going to be. So let's have a look at that. We can define that by looking at the following case. So this is my general, this is the general expression of a complex exponential. Okay. So we have, in fact, our wave function is going to look like this. Let me rewrite it here. So the wave function that we're looking at is the general expression I ML phi plus B minus I ML phi. Okay. And what I'm writing down here is just what this complex exponential looks like. It looks like this, right? And you know, it has a real term and an imaginary term. So what I'm going to do now, I'm going to just plot the real term, because that is the part I can actually visualize. I'm going to draw that as a function of its motion along the ring. So this is, of course, only depicting the real part of this complex exponential. It's a cosine, so it's a wiggling function that goes around the ring. Okay, so as phi grows, it goes around the ring, and that's what I'm kind of like picturing in my mind to kind of understand what this function looks like. So what is the boundary condition of this? Because there's no potential barrier on the ring. Does it just go along and along and along? Well, we can come up with one boundary condition, and that is that if this function is to be a real wave function, it must go around the ring and meet up with the point where it started. Okay, so that means, you see that with the condition here, that if I start at a number phi and I'm going to spin around a full circle, which is 2 pi, then I must end up in exactly the same value that I had at phi. Okay, so it must be symmetric. It must end up with the same number if I make a full circle. The wave function must have the same amplitude if it goes around a full circle, if it meets up with itself again. That is actually a true boundary condition, because that's a condition I put on my wave function, the solution of my wave function. Okay, so we can actually work with this equation, believe it or not, because I can divide the left side by, let's divide it by the following expression. Actually, we can dividing or multiplying. I can divide it by this, which means I multiply it by this expression. Okay, so I'm going to multiply both the left and the right by the negative argument here. So the complex exponential with this negative argument as written here. If you do that, if you multiply both sides by that number, what you'll find is this, okay? So you multiply out basically the effect of phi. The expression on the right becomes 1. And so what I find is the expression below it, which is the complex exponential of I 2 pi ml must equal 1. That is the condition that states that every time you go around a circle, it must meet up with itself, must have the same value. Actually, this is a condition, because what I can see is that this condition is only true if ml is, once again, an integer that starts at 0, plus minus 1, plus minus 2. Every time ml is one of these values, the condition above it is fulfilled. It's basically Euler's formula, right? Every time ml is an integer, any value starting at 1, then this condition is fulfilled. So that means that now I have found my wave function, okay? Now this to kind of illustrate that if ml is not an integer, what it means is that it will spin around and not meet up with itself. And that means that it's not single valued, okay? So the wave function is not single valued if ml is not an integer. So that's why this boundary condition is absolutely important. Okay, so now I have an expression for my particle on the ring, and let's study some of its properties of this particular wave function. Okay, so we have a wave function now, and it has two. Sorry, I should really write it differently. Oops.
Professor, quick question.
Yeah.
Does the ML have anything to do with the ML quantum number, or are they the same thing?
Yeah, the ML is here the quantum number for this particular problem. Like K was the quantum number for the particle in the box. ML serves that function here. So this is my general expression for the wave function. Okay, but now I have a condition on ML. ML must be 0, plus 1, plus negative positive 1, negative positive 2, and so forth. Okay, so yeah, ML serves the same function as K. It is the quantum number for the particle on the ring. So
Okay, cool.
let's consider the following. I see two parts. I'm going to now focus only on this part. And I see that that is very similar to the situation before, where I have two solutions. One is basically motion to the left, and the other one is motion to the right. So I'm going to take one of them and try to kind of normalize this motion. Okay, so what I'm going to try to do is to write the wave function such with an n in the front. Okay, so instead of a, I'm writing m, and I'm trying to normalize this function such that it is fulfilling the Born interpretation of the wave function. That means if I'm going to square this thing, it's going to square this wave function, I get the following. Modulus square of this wave function. It's right here, and I'm going to integrate it on the ring. So that means d phi. I integrate d phi from 0 to pi, because that means that's the whole ring. I have to multiply it by r0, that's the radius, because the integrand is larger when the radius is larger too. So of course the value of the circumference is going to increase as a function of r. That's why you have to put this r as part of the integrand. So don't forget that, that's an important part. So this is the integral I'd like to solve. This one should be 1 for normalized functions, and that's how I can find 1. So let's find this integral, see if we can calculate it. It's going to be r0 n squared, and then simply the integral over this thing, d phi. That's not so hard, actually, because you know, if you take the modulus square of a complex exponential, you simply get 1. Okay, so I basically simply get an integrand that is 1. This is it. Okay, so the integrand of the antiderivative of 1 is going to be x, or phi in this case. I let phi run from 0 to 2 pi. That means the value is going to be 2 pi. Okay, so it's going to be 2 pi r0 n squared equals 1. And that means that I can calculate n, and n is going to be 1 over 2 pi r and then the square root of that. Okay, so that is going to be my normalization constant. So that's good. That means I have now a nice expression for my wave function for the particle on the ring. Here it is, 1 over 2 pi r naught, and then E ml phi. Okay, so that is the motion of a particle in one direction, not two directions, one direction. That's now normalized. All right, well, look at the modulus square of this thing. I find that that is actually simply 2 pi r0. Okay, so that is a constant. That means that for all of these functions, the probability of finding the particle anywhere on the ring is a constant. In other words, it is the same everywhere. Okay, so unlike the particle in the box, the particle in the ring actually is uniformly described, uniformly defined. Okay, so the probability of finding the particle on the ring is uniform. There's no particular location along the ring where you are more likely to find the particle. That sounds like a little counterintuitive, but in fact, you can understand this by the notion that there's no potential barrier. Okay, so there's no reason why the particle should be confined in one particular place along the ring. It's completely symmetric. There's no barrier. That means it is a uniform probability of finding the particle anywhere. The other thing I'd like to point out is the energy. The energy, of course, is related to ml and has the following expression. So you take the expression for ml. ml, of course, is an integer. And so we rewrite this in terms of energy, okay, because ml was defined in terms of energy. So I simply rewrite that same formula and now in terms of energy, and this is what I get. Now compare this with our previous expression for k squared. Okay, so k squared h bar squared 2m. That's what we found for linear motion, translational motion, and it's very similar. Okay, so you see again that ml and k play the same role. The I and the M also play the same role, right? So that's nice. So of course, as we can see here, the energy again is quantized because the ml can only take on certain values. So S, the particle in the box, the particle in the ring, is a quantized system. The energies only take on discrete values defined by ml. ml, once again, is 0, plus minus 1, plus minus 2, and so forth, right? Now, in the important difference here between the particle in the box and the particle on the ring is that, unlike the particle in the box, the lowest value of this quantum number is going to be 0. And that means the lowest possible value of the energy is 0. That is weird. How is that possible? How is it possible that previously I had a 0-point energy which is finite, and now I have a 0-point energy which is not finite? How can I understand that? Well, you can understand that perhaps if you realize that, again, the distribution of the particle in space, the probability of finding the particle in space on the ring, is not necessarily confined. So the confinement on the ring is not the same as confinement in one-dimensional space, linear motion in the box. There, the particle really has to adopt curvature to fit in the box. Here, you don't necessarily have to do that. The lowest order wave function actually has 0 curvature. That means no kinetic energy, and that means that it has a 0-point energy of 0. Okay, so that is different. It's an important difference, and it's directly related to the fact that the particle is not experiencing a potential barrier, and therefore can be in the box with no kinetic energy. Okay, so very important difference. Okay, so let me see. I have a few more things, but I think I'm going to do that next time. Don't want to burden you with too much. Are there any questions at this point about this new situation, particle on the ring? Make sure you see the similarities between the particle on the ring and the particle in the box. Very similar, but also some differences. So understand both the similarities and the differences. The particle on the ring will play an important role for us when we consider the atom. In fact, this wave function that we just solved is going to be part of our general solution for the electron in the atomic system. You will see it will come back, the exact same solutions, plus something else that we will unveil next time. Okay. I'll leave it at that, and we'll continue on Wednesday. Okay. All right. Okay, there's one question about the midterm quiz. Once again, it is open book. Okay, so it means you can have all kinds of printed material in front of you to help you solve the problems. Tables, lists, book can be open, so notes you can have in front of you. What you cannot have is internet connection and look things up. Okay, we don't want you to do that. We also don't want you to communicate with your peers during the quiz. That is not a good idea. That is basically academic dishonesty, and when we detect that, you will be in big trouble. So don't do that. We will probably activate the lockdown browser for that purpose. Okay, and I will send you information about that on Wednesday. So that's how we're going to run it.
The lockdown browser is same as responders, right? Is it the same?
Correct.
Or no?
Correct. Yeah, responders lockdown browser. That's right.
Oh, okay. Thank you.
Sure.
Professor, just once again, the sample midterm gonna be posted today, right?
That is the idea. Yes.
Okay, thank you so much.
Yep.
But what about the solution for that?
The solution will be posted later this week probably on Thursday, because I want you guys to really practice as if it was a real exam and really test what you know, and then we're going to reveal the answers after that.
Sure. Thank you so much.
Professor, I have one more question about the last question of the homework. Could you explain why the answer is third option, not the second one?
Say again, the homework?
Yes, the homework that we just submitted, the third homework.
Of the last question, the right solution, it was B, right?
Yeah.
Right. So you don't understand why the answer is B?
I mean, let me just. For me, I chose B, but the correct answer is C.
Okay, let me stop this recording first.